When you search your computer for a Python script by typing *.py, your system instantly knows what you mean. The asterisk stretches to cover any file name, while a question mark drops perfectly into a single character slot. At its core, matching strings is simple. If the characters match exactly, or if the pattern has a question mark, both pointers step forward together in perfect sync. The friction comes from the asterisk. It is completely unpredictable. It can represent 0 characters, a single character, or an infinitely long text sequence. A single star forces the algorithm to abandon simple character comparison and simultaneously explore multiple alternate realities of matching. The exact moment our pointers encounter a star, the logic splits into 2 distinct decision paths. On path 1, we assume the star matches absolutely nothing. The pattern pointer skips past the star, but the text pointer stays exactly where it is. On path 2, we assume the star consumes the current character. The text pointer moves forward, but the pattern pointer remains locked on the star, holding its position to potentially consume even more. Following these recursive branches eventually leads to a base case. If both strings are reduced to completely empty states at the same time, we hit a valid match. But if the text runs out while the pattern still has characters left, we check for a specific edge case. The state only evaluates to true if the remaining pattern consists entirely of trailing stars, which cleanly vanish into empty sequences. Recursion perfectly maps these branches and edge cases. However, as the strings grow, it recalculates the exact same dead ends endlessly. To scale this, we have to cache our work. This chart shows how we map our sequence to a 2D dynamic programming table. We use one-based indexing, creating an extra 0th row and column to explicitly store the empty string base cases we just established. For an exact character match, or a question mark, the grid follows a strict rule. The current cell simply copies its true or false value from the cell diagonally up and to the left. Think about the 2 recursive paths we traced earlier. If you land on a star, which 2 adjacent cells dictate your outcome? You check the cell directly above, representing the choice to ignore the star, and the cell to the left, representing the choice to consume a character. The matrix turns a massive recursive tree into simple spatial lookups. Notice the structural redundancy in the table. To calculate any value, the algorithm only ever looks at the current row, and the single row immediately preceding it. The rest of the grid is dead weight. We extract those 2 rows and dynamically update them as 1D arrays, iteratively overwriting the old data as we moved on the strings. By analyzing the specific spatial dependencies of the data, we compress the memory footprint from a massive O of n times m grid straight down to an O of m array. This is the optimized Python code executing a highly complex test case loaded with wildcards. The one-to-one matching logic maps precisely into standard if and elif statements. When characters match, the code pulls the Boolean value straight from the previous row array. When evaluating a star, the logic becomes a single Boolean OR statement, checking if either the top array value or the left array value resolves to true. The final architecture delivers a time complexity of O of n times m, while keeping auxiliary space restricted to O of m. You only need 2 rules for the table: pull diagonally for exact matches, and check top or left for stars. Wildcard matching requires you to identify the overlap in chaotic branching logic and methodically compress it into a streamlined architecture. You have the structural blueprint. Open your editor and start coding.